Welcome everyone. I will present our work, Enhancing Develop Interactions with Programming Screencasts through Accurate Code Extraction. Programming screencasts have become a pervasive resource on the internet, which is favored by many developers for learning new programming skills. However, the streaming nature of screencasts limits the choices that developers have for interacting with its content, such as navigating the video and reusing the source code. An intuitive way is to convert the screen images into text using OCR technique, which can be easily searched and indexed and further utilized to build multiple downstream applications. However, we observe three major noises in the extraction process that will dramatically affect the quality of the extracted code. Thus, we built a tool named FSE2Code with two components: denoising code extraction and enhancing video interaction. Given a programming screencast, FSE2Code first extracts source code by 3 steps, then enhances video interaction by leveraging the accurately extracted code. Step 1. Valid code frames identification. Since most of the consecutive frames from the programming screencast are nearly the same, and these highly identical frames are of no use for further analysis, we first remove such non-informative frames by measuring the pixel-level dissimilarity using normalized root mean square error. Here, we set the threshold to 0.05. For example, here, frame 2 and frame 3 will be removed because they don't satisfy the threshold, which suggests that they are too similar to the frame 1, while frame 4 will be retained because it contains enough new information. Next, we further remove frames that do not contain code or the contained code is partially visible. Due to the limitation of annotated data, we fine-tune a pre-trained CNN model as the classifier. This is a programming screencast analyzed by FSE2Code. And we are going to present the results of valid frames identification. There are 74 frames in total. For valid frames, they all have a clear code region. For invalid ones, however, they either have no code region or the contained code is partially visible. Step 2. Code region extraction. To eliminate interferences from non-code regions such as code completion suggestion window and pop-up menu, we crop code editor window from valid code frames. To do so, we detect the candidate boundary lines using candy edge detector. However, the original detection results are very noisy. To reduce the detection noise, we carry out 2 steps of clustering. First, we use dbScan to cluster close-by boundary lines based on their overlap and distance. Interestingly, we further cluster frames with similar window layouts. This level of clustering is very helpful since it can effectively eliminate the differences, which is also considered as noise, between detected edge maps of different frames. Finally, we crop the code editor window based on the filtered edge maps. We are going to present the results of code region detection. All the frames in this video have the same window layout, and the detected code region is precise. Step 3. OCR errors correction. FSE2Code extracts source code from the cropped code region using Google Vision API. Errors are very common in the original OCR code. For example, cursor is wrongly recognized into letter I. We detect these errors by training statistical language models from a large corpus of source code collected from 300 GitHub Java projects as domain-specific spell checkers. Specifically, we build a unigram language model and a line structure model. To correct the detected errors, we leverage cross-frame information, that is, a wrongly recognized code line in one frame might be correctly recognized in another frame. For example, in frame I, a code line is wrongly recognized into properties prop in minus new properties, whose line structure is. Here, IDU and IDL represent for identifiers that with upper and lower characters. However, in frame J, this code line is correctly recognized. So fixing a detected error code line is pretty straightforward. We match it with correct candidate code lines using added distance and replace it with the matched correct counterpart. Here, we present a comparison between the original OCR content and the corrected one. The J frame is wrongly recognized as 2F frame, while in the corrected version, this error is successfully fixed. Here is another type of error. The missing of two brackets result in a wrong line structure, and it is also detected and fixed by PSE2 code. By leveraging the accurately extracted code, our interaction-enhanced video player supports following 4 features. Video analysis. PSE2 code can automatically extract the source code from any programming tutorial on the internet. Search navigate by code. PSE2 code can search for the specific frame and directly navigate the video based on the input query. Files content view. PSE2 code provides watchers a clear view of any code content appeared in the screencast. Action timeline. PSE2 code informs watchers when the tutorial order does what to which file. Next, let's have a look of our developed web prototype. We collected 23 playlists of Java programming tutorial from YouTube. You can select any video that you're interested in. Once click the button, the PSE2 code will automatically start the analyzing process. Once the whole process is finished, you can click the button to watch the enhanced video. All the files are listed for you to have a quick view of any code content. The specific file content is synchronized with video playing. In the action timeline, the timestamp, action type, and detailed information are provided. You can directly navigate the video by clicking the corresponding timestamp. For action switch, you can view the names of source and target files. For action edit, the numbers of inserted and deleted code lines are presented. You can find more detailed information by clicking to expand the summary. For video navigation by code content, you can enter your query here, and the PSE2 code will return a list of timestamps of matched frames. By clicking the timestamp, you can directly navigate the video to an interested frame. In the experimental evaluation, we first evaluate the effectiveness of PSE2 code in denoising code extraction. Then, we conduct a user study to evaluate the applicability of PSE2 code in enhancing developed interactions with programming screencasts. First, we evaluate the effectiveness of 3 main steps in denoising code extraction which are valid code frames identification, code region extraction, and OCR errors correction. To build the testing dataset, we collect 23 most popular playlists for Java tutorial from YouTube, and then randomly sample 2 videos from each playlist, which gives us 46 programming tutorials. Finally, there were 4,828 frames involved in the testing. For the formal 2 steps, we use the approach of Alamadi's work as our baseline, where a YOLO network is applied to identify valid code frames and crop the code region simultaneously. Here, we use the metric intersection over union to measure the accuracy of predicted code region bounding box. In this frame, green bounding box is the annotated ground truth, while the red one is predicted by the model, and the IOU is calculated as dividing the area of overlap between bounding boxes by the area of union. A higher IOU suggests a more accurate predicted bounding box. For OCR errors correction, we calculate the ratio of incorrect words that are corrected by PSE2 code for each frame in the testing set. So now let's ask, how effective is PSE2 code in identifying valid code frames and locating code region? This table shows the comparison results between PSE2 code and the baseline. This column is the accuracy for valid frames identification. These 2 columns are F1 scores for identifying valid and invalid frames respectively. The last column shows the IOU for the predicted code region bounding box. Then we ask, how effective is PSE2 code in correcting OCR errors? The ratio of incorrect and correct words is about 1:3 in the original OCR code, which suggests that OCR errors are very common. 88% of the detected OCR errors can be truly corrected. For those PSE2 code fails to correct, mostly because there were multiple similar words in the code and the PSE2 code fails to choose the correct one. However, only 46% of all the OCR errors can be truly corrected. This is because our trained spell checker fails to distinguish incorrect words from the correct ones in some circumstances. Next, for evaluating the applicability of PSE2 code in enhancing develop interaction, we conduct user study. 3 programming tutorials with different topics are chosen from our dataset, and we design a quiz for each tutorial with 5 questions. To correctly answer these questions, participants must carefully explore the code content, API usage, and other information introduced in the tutorial. 10 participants are randomly divided into 2 groups. Participants in the experimental group use our interaction-enhanced video player, while those in the control group use regular video player. Participants in both groups are asked to answer the same questions and rate the usefulness of the corresponding tool. The ratings are on a 5-point Likert scale, with 5 being the best. So now let's ask, how useful is PSE2 code in enhancing develop interactions with programming screencasts? This table shows the results of a user study. This column presents time that participants use to finish the questions. This column is the correctness of answers that participants give. The last column shows the usefulness ratings given by the participants. The results suggest that participants generally agree that our tool is more helpful for learning knowledge from video tutorials compared to the regular video player, which is also confirmed by the fact that participants in the experimental group do give more correct answers in less time. In conclusion, we explicitly address the 3 noisy challenges in the code extraction process. We develop a tool named PSE2 code to enhance develop interactions with programming screencasts through accurate code extraction. And that's all. Thanks for your attention.